Right now, as you
Still
sit
ticking
there
after all
listening to
these
this,
years.
about
The
100
secrets it
trillion
holds,
neutrinos
buried
are
deep.
passing through your body every single
The
second.
patterns are
They're
converging.
streaming
This
through your
could be it.
skin, through your bones, through
Initiating full
every atom you're
analysis.
made of. They came from the
The
heart
rig
of the
is just
sun,
ahead. We
traveled
need to keep
93
pushing
million
forward.
miles
The
in
data from
8
this
minutes
expedition
and
could
20
change
seconds.
everything.
And they're moving through you at very nearly the speed of light. And not one of them will touch you. Not one. In your entire lifetime, out of the trillions upon trillions that will fly through you, maybe one, just one, will ever make contact with an atom inside your body. Maybe. This is the story of the ghost particle, the story of how we discovered something that barely knows we exist, and the story of the men and women who spent their entire lives trying to catch something that can pass through a light year of solid lead without slowing down. Before we go any further, let's start with something you already understand without thinking about it. You can touch things. You pick up a glass of water and you feel it in your hand. You press your fingers against a table and the table pushes back. You step on the ground and the ground holds you up. This seems obvious. This seems like the most basic, unremarkable fact about reality, but it's actually extraordinary. Understanding why you can touch things is the first step toward understanding why neutrinos can't. Everything around you, the chair you're sitting in, the device, you're listening on your body, the air in the room is made of atoms. You learned this in school. Atoms are the building blocks of all ordinary matter. Every element on the periodic table is defined by its atoms. Hydrogen, the simplest element, has 1 proton and 1 electron. Carbon, the basis of all life on Earth, has 6 protons, 6 neutrons, and 6 electrons. Iron, the element that makes up most of Earth's core, has 26 protons, 30 neutrons, and 26 electrons. There are 92 naturally occurring elements, each with a different number of protons in its nucleus, each with different properties, and all of them built from the same 3 basic components: protons, neutrons, and electrons. An atom has 2 main parts. At the center is the nucleus, a dense clump of protons and neutrons packed together incredibly tightly. Surrounding the nucleus at a much greater distance are the electrons orbiting in complex patterns that quantum mechanics describes, but that nobody truly visualizes. Now here's what's remarkable. The nucleus is tiny, unimaginably tiny compared to the atom as a whole. If you enlarged an atom to the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. The electrons would be like gnats buzzing around the outer seats. Everything in between would be empty space. Pure vacuum, nothing. This means that matter, the stuff you think of as solid, is overwhelmingly nothing. Your body, which feels so substantial, so real, is almost entirely empty space. The atoms that make you up are almost entirely empty space. If you could somehow remove all the empty space from every atom in every human being on Earth, all 8 billion of us, the remaining matter would fit in a volume smaller than a sugar cube. All of humanity, compressed, smaller than a sugar cube. So if atoms are mostly empty space, why does the world feel solid? Why can't you walk through walls? Why can't you pass your hand through the table in front of you? The answer has nothing to do with physical material, blocking physical material. It's because of a force, a fundamental force of nature, and that force is the electromagnetic force. When you press your hand against the table, the electrons surrounding the atoms in your skin repel the electrons surrounding the atoms in the table surface. This electromagnetic repulsion creates a barrier that your hand cannot penetrate. The electrons in your hand never actually touch the electrons in the table. They just get close enough that the electromagnetic force between them becomes overwhelmingly strong. Nothing is actually touching in the way you intuitively imagine. It's all forces, all fields, all electromagnetic interactions at a distance. The solidity of everything you have ever touched is an electromagnetic illusion. Real in its effects, absolutely real, but fundamentally a product of charged particles pushing against each other across empty space. This is important because it leads us to something essential. The universe operates through 4 fundamental forces. Just 4. Every interaction between every particle in the entire cosmos is governed by one or more of these 4 forces. Understanding them is critical to understanding neutrinos because what makes neutrinos so extraordinary is which of these forces they respond to and which they ignore entirely. The first force is gravity. Gravity is the one you know best. It's the force that keeps your feet on the ground, that keeps the Earth in orbit around the sun, that holds galaxies together. Gravity acts on anything that has mass or energy. It has infinite range. It reaches across the entire observable universe. The sun's gravity holds Neptune in orbit at a distance of nearly 3 billion miles. The Milky Way's gravity holds its hundreds of billions of stars together across a span of 100,000 light years. But here's the thing about gravity that most people don't appreciate. It's weak, incredibly, almost absurdly weak. It seems strong because you're standing on a planet with a mass of about 6 trillion kilograms, and all that mass is pulling you down. But the gravitational attraction between two individual subatomic particles is essentially nothing. The gravitational pull between two protons is roughly 10 to the 36th power times weaker than the electromagnetic force between them. That's a 1 followed by 36 zeros, a number so large it becomes meaningless. Gravity matters at cosmic scales because it always attracts, it never cancels out, and it adds up over enormous amounts of matter. But at the scale of individual particles, gravity is irrelevant. It's the weakest force in the universe by an almost incomprehensible margin. The second force is the electromagnetic force. This is the force that actually governs your daily life far more than gravity does, even if you don't realize it. The electromagnetic force acts between particles that carry electric charge. Protons carry positive charge. Electrons carry negative charge. Opposite charges attract, like charges repel. This is the force that holds atoms together. The positive protons in the nucleus attract the negative electrons, keeping them bound in their orbits. It's the force that holds molecules together through chemical bonds. It's the force responsible for all of chemistry and all of biology. When you see light, you're detecting electromagnetic radiation. When you listen to a radio, you're picking up electromagnetic waves. When your nerve cells fire, they're using electromagnetic signals. Every color, every sound, your ears convert from pressure waves transmitted through electromagnetically bonded air molecules. Every sensation of touch or heat, all of it is electromagnetic. This force has infinite range like gravity, but it's vastly stronger at the particle scale. The electromagnetic force is what makes the world tangible. It is the reason things feel real. The third force is the strong nuclear force, sometimes just called the strong force. This is the most powerful force in the universe, but it operates over an incredibly short range, only about the width of an atomic nucleus, roughly 10 to the negative 15th meters. That's about 1/quadrillionth of a meter. Beyond that distance, the strong force effectively ceases to exist. The strong force is what holds the nucleus together. Think about this for a moment. Protons are all positively charged. They should repel each other electromagnetically with tremendous force. A nucleus with two or more protons should fly apart instantly because of the electromagnetic repulsion. But it doesn't, because the strong force overpowers the electromagnetic repulsion at these tiny distances. The strong force binds quarks together to form protons and neutrons, and it binds those protons and neutrons together to form nuclei. Without it, no nucleus heavier than hydrogen could exist. There would be no carbon, no oxygen, no iron, no rocky planets, no life. The strong force is the reason matter has the complexity it does. And then there's the fourth force, the weak nuclear force. This is where our story truly begins. The weak force is unusual compared to the other three. It doesn't hold anything together. It doesn't attract particles to each other the way gravity and electromagnetism do. It doesn't bind structures the way the strong force does. Instead, the weak force is responsible for transformation. It allows one type of particle to change into another type. The weak force is what drives a specific kind of radioactive decay called beta decay, where a neutron inside a nucleus transforms into a proton, emitting an electron, and as we'll discover, a neutrino in the process. The weak force operates over an even shorter range than the strong force. Its effective range is about 10 to the negative 18th meters, roughly 1,000 times smaller than the diameter of a proton. If a proton were the size of a city, the weak force would reach across a single room inside one building. That's how limited its range is. The weak force is also true to its name, much feebler than both the strong force and the electromagnetic force at the particle scale. It's stronger than gravity between individual particles, but compared to the other two forces that govern atomic and nuclear physics, it is remarkably feeble. Now here's the crucial point. Different particles respond to different forces. What determines how a particle behaves, how it interacts with the world around it, is which forces it feels. Protons feel all four forces. They have mass, so gravity acts on them. They have electric charge, so electromagnetism acts on them. They contain quarks, so the strong force acts on them. And they participate in weak interactions. Protons are thoroughly sociable particles. They interact with everything. Electrons feel three of the four. They have mass, so gravity acts on them. They have electric charge, so electromagnetism acts on them. They participate in weak interactions. But they don't contain quarks, so the strong force doesn't act on them directly. Still, 3 out of 4 forces is plenty. Electrons interact readily with the world. And then there are neutrinos. Neutrinos are in a category almost by themselves. They have a tiny amount of mass, so technically gravity acts on them. But their mass is so minuscule that this gravitational interaction is utterly negligible for any practical purpose. They have no electric charge whatsoever. Zero. This means the electromagnetic force, the force that governs almost everything in your daily experience, the force responsible for chemistry, biology, light, and the solidity of matter simply does not apply to neutrinos. They are blind to it. It doesn't see them. They don't see it. They also don't contain quarks, so the strong nuclear force has no hold on them either. The only force through which neutrinos can meaningfully interact with other matter is the weak nuclear force, the one force with the shortest range and the lowest interaction probability. This single fact is why neutrinos are ghosts. This is complex because reality is complex. You're understanding this correctly. Take your time. It will all connect. The story of how we came to know about neutrinos begins with a crisis in physics. In the early 20th century, physicists were carefully studying beta decay. In this process, a radioactive nucleus emits an electron and transforms into a different element. For example, a carbon-14 nucleus decays into nitrogen-14. One of its neutrons has turned into a proton and an electron flies out. The problem was energy conservation. The total energy before a reaction must equal the total energy after. This is one of the most fundamental laws in all of physics. It's not a suggestion, it's not an approximation that works most of the time. It's an absolute rule verified in every experiment ever conducted, a cornerstone of the entire edifice of physics. If energy conservation fails, almost everything we know about the universe comes into question. But when physicists precisely measured the energy of the electrons emitted in beta decay, they found something deeply disturbing. The electrons didn't all come out with the same energy. They had a continuous spectrum of energies ranging from nearly zero up to some maximum value. This was wrong, profoundly wrong. If a specific nucleus decays into a specific product nucleus and emits one electron, the energy balance should be exact. The starting energy is fixed. The ending energy is fixed. The electron should carry away the difference, always the same amount every single time. But measurements showed otherwise. Some electrons came out fast, carrying nearly all the available energy. Others came out slow, carrying barely any, and everything in between. A smooth, continuous distribution of energies. It was as though the universe were randomly deciding for each individual decay how much energy to give the electron. Sometimes a lot, sometimes a little with no apparent pattern or reason. The implications were alarming. If the electron was carrying less than the full available energy, where was the rest going? Physicists checked for gamma rays, high-energy photons that might be carrying away the missing energy. They found none. They checked for recoil energy in the nucleus itself. The numbers didn't balance. No matter how carefully they measured, no matter how precisely they accounted for every form of energy they could think of, there was always some energy unaccounted for. It simply vanished. The books didn't balance. And in physics, the books must always balance. This was a genuine crisis in the foundations of physics, not a minor discrepancy, not a measurement artifact, but a fundamental challenge to one of the most sacred principles in all of science. Some brilliant physicists, including Niels Bohr, one of the fathers of quantum mechanics, suggested that perhaps energy conservation simply didn't hold at the subatomic level. Maybe it was only an approximate rule valid statistically for large collections of atoms, but not for individual nuclear reactions. Bohr was willing to abandon conservation of energy. That's how serious the problem was. When one of the greatest physicists in history is prepared to throw out one of the most fundamental laws in physics, you know the situation is desperate. One physicist in particular found this idea intolerable. His name was Wolfgang Pauli Brenner, an Austrian theoretical physicist 30 years old in December of 1930, known for his extraordinary intellect and his famously sharp tongue. He once dismissed a colleague's theory as not even wrong, meaning it was too vague to be tested, too ill-defined to even rise to the level of being incorrect. Pauli Brenner refused to abandon energy conservation. In December of 1930, he wrote a now famous letter to a group of physicists attending a conference in Tübingen, Germany. He couldn't attend himself. He was occupied elsewhere, but he sent the letter. He addressed them as "Dear radioactive ladies and gentlemen," and proposed what he called a desperate remedy. He suggested that during beta decay, alongside the electron, another particle was being emitted. A particle so elusive, so reluctant to interact with anything, that no instrument could detect it. This particle, Pauli Brenner argued, carried away the missing energy. It had to be electrically neutral because the electric charges already balanced without it. It had to have very little mass, possibly none, because the maximum energy of the emitted electrons nearly accounted for all the available energy. And it had to interact extraordinarily weakly with matter, because nobody had ever seen any trace of it. Pauli Brenner initially called this hypothetical particle a neutron, but that name was soon claimed by the much heavier neutral particle James Chadwick discovered inside atomic nuclei in 1932. The particle needed a new name. In Rome, an Italian physicist named Enrico Fermi-Moretti was intrigued by Pauli Brenner's idea. Fermi-Moretti was brilliant, methodical, and unafraid of bold theoretical leaps. In 1933, he took Pauli Brenner's desperate remedy and gave it a name. He called it the neutrino, which in Italian means little neutral one. But Fermi-Moretti did far more than just name it. In 1933 and 1934, he developed a comprehensive theoretical framework for beta decay that incorporated the neutrino and described how the weak force operated. His theory explained how a neutron could transform into a proton while emitting an electron in a neutrino. It was elegant, mathematically precise, and turned out to be remarkably accurate, but it depended entirely on a particle that no one had ever directly observed. At a physics conference in 1934, Fermi-Moretti stood at a chalkboard covered in equations. He explained the mathematics. He showed how the neutrino solved every problem. The audience listened, impressed by the rigor of the theory, but skeptical of its central claim. One physicist stood up. "Beautiful theory, Enrico, but can you catch this ghost?" Fermi-Moretti paused. He looked at the chalkboard, then back at the audience. "Not yet," he said quietly. "Maybe not ever." And the challenge was stark. How do you detect a particle that barely interacts with anything? Pauli Brenner himself was deeply pessimistic. He reportedly bet a case of champagne that his particle would never be found. He later said he had committed a terrible thing by proposing a particle that could never be observed experimentally. And for a long time, it seemed like he might be right. The years stretched on. The 1930s passed. Fermi-Moretti's theory gained acceptance because it explained beta decay so well. But the neutrino at its heart remained invisible. The 1940s came and went, a decade dominated by war and the development of nuclear weapons work that deepened understanding of nuclear reactions, but brought physicists no closer to catching Pauli Brenner's ghost. The technology simply didn't exist. Detecting a particle with such an absurdly small interaction probability required either an incredibly intense source of neutrinos or an incredibly massive detector, or both. In the 1930s and 40s, neither was available. But then everything changed. By the early 1950s, the situation had shifted dramatically. Nuclear reactors developed as part of the Cold War nuclear programs provided exactly the kind of intense neutrino source that was needed. A nuclear reactor is essentially a controlled chain reaction of uranium fission. Each fission event produces several neutron-rich fragments that undergo beta decay. And each beta decay produces a neutrino, or more precisely, an antineutrino. A large reactor produces an almost inconceivable number of these particles. The flux near a powerful reactor core reaches roughly 10 trillion antineutrinos per square centimeter per second. That's 10 followed by 12 zeros every second. Through every square centimeter. It's an enormous number of neutrinos concentrated in a relatively small area. If you could put a big enough detector close enough to a reactor, statistics might finally work in your favor. Even with a probability of interaction close to zero for any individual neutrino, the sheer torrent of particles might produce a few detectable events. Two American physicists saw this opportunity and seized it. Frederick Rhinus Caldwell and Clyde Cowan Montgomery designed an experiment to detect antineutrinos were produced by the Savannah River nuclear reactor in South Carolina. Their approach relied on a process called inverse beta decay. On extremely rare occasions, an antineutrino would interact with a proton in a tank of water via the weak force converting the proton into a neutron and producing a positron, the antimatter counterpart of the electron. The positron would immediately annihilate with a nearby electron, creating two gamma rays flying off in opposite directions. The neutron would bounce around briefly before being captured by a cadmium nucleus dissolved in the water, which would then emit its own distinctive gamma rays after a brief delay. These two bursts of gamma rays, separated by a tiny but measurable time gap of a few microseconds, created a unique signature. A double pulse of light with a specific timing pattern that could be distinguished from random background events. It was a masterpiece of experimental design. The double pulse signature was the key. Random background events could produce a single gamma ray easily enough. Radioactive contaminants, cosmic rays, countless sources of noise. But producing two gamma ray bursts with exactly the right energies, separated by exactly the right time delay, was something that almost only a genuine antineutrino interaction could do. This gave Reines-Caldwell and Cowan-Montgomery a way to pick out the incredibly rare signal from the overwhelming background noise. Months of painstaking data collection followed. Background noise had to be carefully measured and subtracted. Every possible source of false signals had to be accounted for. They ran the experiment with the reactor on and with the reactor off. If the signal was really from reactor neutrinos, it should appear when the reactor was running and vanish when it was shut down. And that's exactly what they found. The signal was there. Clear, consistent, unmistakable. It appeared when the reactor was on. It disappeared when the reactor was off. The ghost had been caught. In June of 1956, Reines-Caldwell and Cowan-Montgomery sent a telegram to Wolfgang Pauli Brenner. The message was simple. We are happy to inform you that we have definitely detected neutrinos. Pauli Brenner was attending a conference in Zurich when the telegram arrived. He opened it in front of his colleagues. He read it aloud, his hands shaking slightly. There was silence. Then thunderous applause. Someone brought champagne. The champagne Pauli Brenner had bet against this very outcome, against the possibility that his desperate remedy could ever be proven real. He drank it, tears in his eyes. 26 years, he said quietly. The ghost is real. The particle he had proposed out of desperation in December of 1930, the particle he feared could never be found, had been observed. Energy conservation was saved. The desperate remedy had been real all along. Frederick Reines-Caldwell received the Nobel Prize in Physics in 1995 for this discovery. Clyde Cowan-Montgomery had died in 1974 and could not share the honor as the Nobel Prize is not awarded posthumously. But the discovery stood. The neutrino existed. Wolfgang Pauli Brenner died 2 years later in 1958 at the age of 58. He had lived long enough to see his ghost proven real, to drink the champagne to know that his desperate remedy had saved the most fundamental law in physics. You've absorbed a lot of information. That's correct. Take the time you need. It will connect. You have the tools. So what exactly is a neutrino? Let's establish this precisely because it matters for everything that follows. A neutrino is a fundamental particle, meaning it is not made of anything smaller. As far as we know, it's not composed of quarks like protons and neutrons. It's not a composite structure. It's elementary, indivisible, a basic building block of reality. A neutrino belongs to a family of particles called leptons. There are 6 leptons in total, arranged in 3 pairs called generations. The first generation contains the electron and the electron neutrino. The second contains the muon, a heavier cousin of the electron, and the muon neutrino. The third contains the tau particle, heavier still, and the tau neutrino. These 3 types, electron and neutrino, muon neutrino, and tau neutrino, are called the 3 flavors of neutrinos. Each one is associated with its corresponding charged lepton. For decades after Pauli Brenner's proposal, physicists assumed neutrinos were completely massless. The original standard model of particle physics, the mathematical framework that describes all known fundamental particles and their interactions, assigned neutrinos 0 mass. This seemed reasonable. No experiment had ever measured a neutrino mass, and the theory worked perfectly well without one. But as we'll discover, that assumption turned out to be wrong. Neutrinos do have mass, but it's so unimaginably small that we still haven't pinned down the exact value. The best current limits suggest the combined mass of all 3 neutrino flavors is less than about 1/10 of an electron volt. The electron, the lightest commonly discussed particle, has a mass of about 511,000 electron volts. That means neutrinos are at minimum several million times lighter than an electron. They are the lightest known massive particles in the universe. Neutrinos carry no electric charge and no color charge. The color charge is the property that allows particles to feel the strong force. We've already seen what this means. The electromagnetic force and the strong nuclear force, the 2 forces that govern almost everything about how matter behaves, simply have no hold on them. But it's worth pausing on just how total this exclusion is. A neutrino cannot emit or absorb a photon. It cannot interact with an electric field or a magnetic field. It is completely invisible to every detector that relies on electromagnetic interactions, which is essentially every detector humans have ever built for any purpose. It cannot feel the force that holds nuclei together. The only door left open to it is the weak nuclear force. a force mediated by carrier particles so heavy that its effective range barely extends beyond the boundaries of a single nucleon. A neutrino moves through the universe interacting only through the weakest relevant force over the shortest relevant distance. It simply lacks the properties that would allow the universe's other forces to take hold of it. Let me explain why the weak force is so catastrophically weak, because the numbers when you work them out are among the most astonishing in all of science. Every fundamental force is transmitted by carrier particles, also called gauge bosons. These carriers are what actually mediate the interaction between two particles. For electromagnetism, the carrier is the photon. Photons are massless, and this is why the electromagnetic force has infinite range. A massless carrier can exist for as long as it needs to and travel as far as it needs to. There's no energy cost to creating a virtual photon that mediates an electromagnetic interaction regardless of distance. This is why two magnets can attract or repel each other from across a room, and why the sun's light reaches all the way to Earth and beyond. For the weak nuclear force, the carriers are three particles: the W plus boson, the W minus boson, and the Z boson. And here is the critical difference. These bosons are not massless. They are enormously heavy. The W bosons have a mass of about 80.4 giga-electron volts each. The Z boson has a mass of about 91.2 giga-electron volts. To put that in perspective, a proton has a mass of about 0.938 giga-electron volts. The W and Z bosons are roughly 80 to 90 times heavier than a proton. They are among the heaviest elementary particles ever discovered. The mass of the carrier particle directly determines the range of the force it mediates. This isn't a rough rule of thumb. It's a precise consequence of quantum mechanics, specifically the Heisenberg uncertainty principle. The uncertainty principle tells us that nature allows brief violations of energy conservation, but only for extremely short periods of time. A virtual particle can borrow energy from the vacuum to pop into existence, but the more energy it borrows, that is, the more massive the virtual particle, the less time it's allowed to exist before it must be reabsorbed. Since even a virtual particle can't travel faster than the speed of light, a short existence means a short distance traveled, which means a short range for the force. For the massless photon, the borrowed energy is essentially zero. The allowed time is essentially infinite. The range is infinite. For the W and Z bosons, the borrowed energy is enormous, roughly 80 to 90 times a proton's mass worth of energy, and the allowed time is fantastically brief. When you work out the numbers, you get exactly the range we encountered earlier, about 10 to the negative 18th meters. 1 atometer, 1 quintillionth of a meter. The enormous mass of the weak force carriers is the reason the weak force barely reaches beyond the boundaries of a single nucleon. Let that settle for a moment. A proton is already incomprehensibly small. You could line up roughly 40 billion protons across the width of a single human hair. And the weak force operates over a distance 1,000 times smaller than that. For a neutrino to interact with another particle through the weak force, the neutrino must pass within about 10 to the negative 18th meters of that particle. It essentially has to score a direct hit on a target that is 1,000 times smaller than the nucleus of an atom. And the nucleus itself is already 100,000 times smaller than the atom. Now think about what a neutrino encounters when it enters a block of matter. Let's say it's flying through your body, or through a wall, or through the entire planet Earth. It encounters vast numbers of atoms. Your body alone contains roughly 7 billion atoms, but each of those atoms is overwhelmingly empty space. The nucleus sits at the center, occupying a volume that is about 1/4 of the atom's total volume. And the weak force target within that nucleus, the region where the neutrino would need to pass to have any chance of interacting, is 1,000 times smaller still. The neutrino flies through atom after atom after atom, passing through the cavernous empty space within each one. Even when it passes close to a nucleus, close isn't close enough. It needs to pass within 10 to the negative 18th meters of a quark or other weak force-sensitive particle. And the probability of that happening on any given encounter is almost vanishingly small. Let's put specific numbers on this. Physicists quantify interaction probability using a concept called a cross-section. Despite the name, this isn't literally the cross-sectional area of a particle. It's the effective target area that a particle presents for a particular type of interaction. For a solar neutrino one with an energy of a few million electron volts interacting with a nucleon, the cross-section is approximately 10 to the negative 44th square centimeters. Let me try to convey how small that is. If you were to write this number as a decimal, you would write a 0, then a decimal point, then 43 more zeros, and only then would you write the first non-zero digit. Compare this to the strong force cross-section of 10 to the negative 26 square centimeters. The weak interaction cross-section is roughly 10 to the 18th times smaller. That's a factor of a billion billion. A billion billion times smaller than a target that's already the size of an atomic nucleus. This leads to one of the most striking thought experiments in all of physics. Imagine constructing a wall of solid lead, not an ordinary wall, a wall that extends for 1 light year. 1 light year of solid lead, roughly 9.46 trillion kilometers. Atom after atom after atom packed together in a continuous barrier of one of the densest elements on Earth. If you fired a beam of neutrinos at this wall, neutrinos with energies typical of those produced by the sun, approximately half of them would pass through the other side completely unscathed. Half. A light year of solid lead, and it only manages to stop roughly half the neutrinos. The other half emerge from 9.46 trillion kilometers of solid matter as if nothing happened, as if the wall weren't there at all. This is not magic. This is not a violation of physics. This is pure probability. The laws of physics absolutely permit a neutrino to interact with a lead atom through the weak force. It happens. We measure it in our detectors every day. But the probability of any single neutrino interacting with any single atom is so unfathomably low that even stacking up atoms for a light year doesn't guarantee an interaction. The universe built a particle whose interaction probability is so small that practically infinite amounts of matter are functionally transparent to it. Right now, the sun is a thermonuclear furnace of almost incomprehensible scale, deep in its core where the temperature reaches about 15 million degrees Celsius, and the pressure is roughly 265 billion times the atmospheric pressure on Earth's surface. Hydrogen nuclei are being fused together into helium. This process, called the proton-proton chain, releases energy in the form of photons and kinetic energy. But it also produces neutrinos, specifically electron neutrinos. Every time certain fusion reactions occur, and they occur constantly, trillions upon trillions of times every second, neutrinos are emitted as a byproduct. The sun generates roughly 2 times 10 to the 38th neutrinos every second. That's 200 billion neutrinos pouring out of the sun's core every single second, streaming outward in all directions at very nearly the speed of light. By the time these neutrinos reach Earth about 8 minutes and 20 seconds later, they've spread out over an enormous sphere with a radius of 150 million kilometers. But even spread out across this vast distance, the flux at Earth is staggering. About 65 billion solar neutrinos pass through every single square centimeters of area facing the sun every single second. Hold up your thumbnail. That's roughly 1 square centimeter. 65 billion neutrinos just flew through it, and they didn't stop when they entered your thumbnail. They continued straight through your hand, through your arm, through your torso, through the chair you are sitting in, through the floor, through the foundation of the building, through the bedrock below, through the mantle, through the liquid iron outer core, through the solid iron inner core, through the mantle on the other side, through the crust, through the ocean or land surface, on the far side of the planet, and out into space again, without slowing down, without being deflected, without interacting with a single atom in the entire 12,700-kilometer journey through the body of a planet. During the day, these neutrinos arrive from above from the direction of the sun. At night, they come from below. They've already passed through the entire Earth to reach you. Day and night unceasing, you are bathed in a continuous flood of neutrinos that you will never feel. They have been passing through you since the moment you were born. They passed through the hospital where you were born. They passed through every building, every mountain, every ocean. They passed through the moon. They passed through Jupiter. Nothing in the solar system presents a meaningful obstacle to them. There's a beautiful illustration of the contrast between neutrinos and photons that makes the whole picture vivid. Consider a photon and a neutrino produced side by side in the same nuclear fusion reaction at the center of the sun. They're born at the same moment, in the same place, from the same event. The neutrino, interacting only through the weak force, flies straight outward through the sun's interior. It passes through roughly 700,000 kilometers of incredibly dense stellar plasma matter, so compressed that the core density is about 150 times the density of water without interacting. It exits the sun about 2 seconds after being created. It then crosses the 150 million kilometer gulf between the sun and Earth in about 8 minutes and 18 seconds. Total travel time from creation to your eyeball, about 8 minutes and 20 seconds. The photon has a very different journey. It interacts electromagnetically, which means it's constantly being absorbed and re-emitted by the charged particles in the sun's interior. It bounces from atom to atom, scattering in random directions, taking a tortuous random walk outward through the solar interior. On average, a photon scatters after traveling only about 1 centimeter before it's absorbed and re-emitted by another atom. 1 centimeter at a time in a random direction each time across 700,000 kilometers of solar material. The result is that the average photon takes an estimated 170,000 years to random walk from the core to the surface. 170,000 years for the photon. 2 seconds for the neutrino. Same starting point, same solar material. But the photon interacts electromagnetically and the matter is opaque to it. The neutrino interacts only through the weak force, and the same matter is perfectly transparent. This contrast captures everything. The electromagnetic force makes matter opaque to photons. The strong force makes nuclear material opaque to hadrons. But the weak force, with its absurdly short range and its enormously heavy carrier particles, makes the interaction probability so small that matter is essentially invisible to neutrinos. A neutrino can fly through a star in seconds. It can fly through a planet without noticing. It can fly through a light year of solid lead and have a coin flip chance of emerging from the other side. The neutrino follows every law of physics with perfect fidelity. It's not breaking any rules, it's simply exploiting a loophole that most particles can't access. And yet we've caught it. We've detected this particle that passes through planets and stars. We've measured its properties. But catching neutrinos from a reactor is one thing. What physicists really wanted was to catch neutrinos from the sun, to prove that the fusion reactions we believed were powering the sun were actually happening, to touch the sun's heart. And one man decided to spend 3 decades of his life trying. His name was Raymond Aldrich Davis, and he was about to descend into darkness. You've covered substantial ground. The complexity is intentional because reality is complex. The next section will connect these pieces. You're prepared for what's coming. In April of 1964, a man stood at the entrance to an elevator shaft carved into rock. Raymond Aldrich Davis was 46 years old, an American chemist and physicist. Methodical, patient to the point of obsession, driven by a quiet faith in precision that bordered on religious conviction. He had spent the years after the Second World War working at Oak Ridge National Laboratory in Tennessee, then moved to Brookhaven National Laboratory on Long Island in the early 1950s, developing techniques for detecting trace amounts of radioactive isotopes. The work required extraordinary patience and meticulous attention to detail. Davis excelled at both. By 1964, he had left the stability of Brookhaven to pursue what most of his colleagues considered a fool's errand. He was about to descend nearly 5,000 feet underground into an abandoned gold mine in the Black Hills of South Dakota to hunt for something that most people believed could never be caught in meaningful quantities: solar neutrinos. The elevator creaked as it began its descent into the Homestake mine in Lade, South Dakota. Darkness closed around him like a fist. The air grew colder. The walls of the shaft, rough-hewn from ancient rock, glistened with moisture in the dim light of the elevator's single bulb. The smell was distinct minerals and damp stone, and time itself compressed into a scent. The only sound was the grinding of ancient machinery and the drip of water somewhere in the absolute black. 1,500 meters down, 1.47 kilometers beneath the surface of the Earth. Deeper than most mines in the world. Deep enough that the cosmic radiation that constantly bombards the surface would be blocked by the sheer mass of rock overhead. When the elevator finally stopped and the gate opened, Davis stepped out into a cavern that had been carved from solid rock decades earlier by miners searching for gold. The walls glistened with moisture. The temperature was constant, cool but not freezing. The silence was profound, broken only by the occasional creak of settling rock and the distant sound of water finding its way through invisible cracks. And there in the center of the cavern sat a massive cylindrical tank, 615 metric tons of perchloroethylene, ordinary industrial dry cleaning fluid. One of his assistants, a young engineer named Thomas, stood beside the tank with a wry smile. "We're looking for God's fingerprints in a laundromat, Ray." Davis didn't smile. He walked up to the tank and placed his hand on the cold metal surface. The steel was smooth, slightly damp from the humidity of the mine. "No," he said quietly, "we're looking for the sun's heartbeat." The detector Davis had built was unglamorous to the point of being almost absurd. There were no gleaming instruments, no blinking panels of electronics, no complex arrays of sensors. It was essentially a very large, cylindrical vat of solvent sitting in a cavern carved out of rock, connected to some pumping equipment, and chemical extraction apparatus. Visitors to the mine who saw it for the first time were sometimes baffled. This was supposed to detect particles from the sun, a tank of cleaning fluid in a hole in the ground. But its design was brilliant. The choice of material was not arbitrary. It was the product of careful theoretical calculation about which nuclei would be most sensitive to the particular energies of solar neutrinos. Perchloroethylene contains chlorine, and specifically the isotope chlorine-37, which makes up about 1/4 of all natural chlorine. On extraordinarily rare occasions, a solar neutrino would interact with the chlorine-37 nucleus through the weak force, transforming it into an argon-37 nucleus and emitting an electron. This reaction, called the inverse beta decay of chlorine-37, was the detection mechanism. Each time it occurred, one atom of chlorine-37 would become one atom of argon-37. Davis's job was to count the argon atoms, pause and consider the absurdity of this task. He had 615 metric tons of fluid. That's roughly 2,380,000 liters. An Olympic swimming pool holds about 2.5 million liters. You're talking about a volume roughly comparable to a large swimming pool, but instead of water, it's filled with cleaning solvent. In this enormous volume, the sun's neutrino flux was predicted to produce, on average, roughly 1 or 2 argon-37 atoms every single day. 1 or 2 atoms per day in 615 tons of liquid. It would be like trying to find one specific grain of sand that had been secretly added to a swimming pool full of sand. Except the grain is an atom invisible to the naked eye, indistinguishable by sight or touch, and the swimming pool is the size of a small building. Finding it required chemical techniques of extraordinary sensitivity, the kind of work that demanded not just scientific knowledge, but something closer to artistry. Davis ran the experiment in cycles lasting several weeks. He would let the detector sit undisturbed, quietly accumulating argon atoms from the rare neutrino interactions. The tank was sealed. No air could get in or out. The cleaning fluid sat in darkness a mile beneath the surface, waiting for neutrinos from the sun to occasionally, against astronomical odds, strike a chlorine nucleus. Then, after weeks of accumulation, he would flush helium gas through the entire tank. The helium would carry the tiny number of volatile argon atoms out of the liquid. These atoms would be swept along with the helium into collection vessels. Next came extraction through painstaking chemical separation. The helium containing the argon would be processed through a series of purification steps, removing every contaminant, isolating the argon with extreme care. Finally, he would place the argon sample in a small proportional counter, a device that could detect the radioactive decay of individual argon-37 atoms as they converted back to chlorine-37. Argon-37 has a half-life of 35 days. It decays by capturing an electron from its own electron cloud, converting back into chlorine-37, and emitting a characteristic burst of energy. By counting these decays over a period of months, Davis could determine how many neutrino interactions had occurred during the exposure period. Each complete measurement cycle, from closing the tank to flushing it, extracting the argon, purifying it, and counting the decays, took the better part of a year. The statistical uncertainties were large because the numbers were so small. A handful of atoms here, a handful there. Sometimes 8 atoms in a cycle, sometimes 12, sometimes 6. Davis needed many cycles, many years of data to build up enough statistics to say anything definitive. His wife Margaret visited the mine once in the early years. She stood in the cavern, looking at the tank, trying to understand why her husband had uprooted their lives for this. "How long will this take, Ray?" she asked. He looked at the tank for a long moment before answering. "As long as it takes, Margaret. As long as it takes. You don't need to remember every detail here. The pattern is what matters. One man on one tank, counting individual atoms over the course of decades. Hold that image. The patience is what's important." In 1968, after 4 years of operation, Davis published his first results. He had found argon atoms, definitive proof that solar neutrinos were reaching his detector and occasionally, against all odds, interacting. The experiment worked. The neutrino Pauli Brenner's ghost particle was being caught in a vat of dry cleaning solvent a mile underground. This was a triumph. This was vindication of the entire approach. But there was a problem. Davis found only about 1/3 as many argon atoms as theorists had predicted. Solar models built on decades of work, understanding nuclear fusion in the sun's core, predicted a certain rate of neutrino interactions based on the temperature, density, and composition of the solar interior. Davis was measuring roughly 1/3 of that predicted rate. 2/3 of the expected neutrinos appeared to be missing. This discrepancy became known as the solar neutrino problem, and it was one of the most stubborn and perplexing puzzles in physics for the next 3 decades. It gnawed at the field. It divided physicists into camps. It spawned hundreds of theoretical papers, dozens of proposed explanations, and years of heated debate at conferences around the world. Because the discrepancy struck at something fundamental. Either we didn't understand how the sun works, which would mean our models of stellar physics were deeply flawed, or we didn't understand neutrinos, which would mean our standard model of particle physics was incomplete. Both possibilities were deeply uncomfortable. Both had enormous consequences. The stakes were high because the solar model wasn't just some rough sketch. It was one of the most carefully constructed and thoroughly tested models in all of astrophysics. Decades of work had gone into understanding stellar interiors, the temperatures, pressures, densities, energy transport mechanisms, nuclear reaction rates, and compositions. The solar model successfully predicted the sun's luminosity, its radius, its surface temperature, and the frequencies of its oscillation modes, which had been measured with extraordinary precision by helioseismology, the study of vibrations in the sun's interior. It was not a model that seemed likely to be wrong by a factor of 3, and yet Davis kept getting the same answer. Year after year, cycle after cycle, he extracted his argon atoms and counted them, and the number was always about 1/3 of what the theorists said it should be. The attacks came swiftly. Some physicists questioned his methods. Some wondered if his chemical extraction was inefficient, if he was losing argon atoms during the process and undercounting. Davis tested this methodically. He injected known quantities of argon into his tank and extracted them. He ran the full procedure with argon he had added himself. He consistently recovered more than 90%. The extraction was working. The chemical process was sound. The deficit was real. Other physicists scrutinized the solar models. Maybe the core temperature was slightly lower than calculated. A small change in temperature could significantly affect the rate of certain fusion reactions and thus the neutrino production rate. Solar physicists examined this possibility, meticulously adjusting parameters, refining their inputs, testing sensitivity to various assumptions. The models were robust. You could tweak parameters within their allowed ranges and reduce the predicted neutrino rate somewhat, but not by a factor of 3. Not by the amount Davis was seeing. The discrepancy persisted stubbornly, no matter how you adjusted the model within reasonable bounds. In 1975, at a major physics conference in Irvine, California, a young theoretical physicist stood up during Davis's presentation. Davis had just shown his latest data, 7 years of measurements, 47 complete extraction cycles, all showing the same result, roughly 1/3 the predicted rate. The young physicist's voice carried an edge of barely concealed contempt. "Dr. Davis," he said, "have you considered that perhaps the problem is not with the sun, but with your experiment, that you simply don't know how to count atoms correctly?" The room went silent. Several hundred physicists, the audience uncomfortable, waiting to see how Davis would respond. Davis, standing at the podium with his slides behind him, looked at the young physicist for a long moment. His expression didn't change. His voice when he spoke was steady, controlled, without anger. "I've run this experiment 47 times," Davis said. 47 complete cycles over 7 years. Same procedure every time. Same result every time. I've tested the extraction efficiency with known samples dozens of times. It works. The recovery rate is above 90%. The argon is there. I'm counting it correctly." He paused. "I'm measuring what's actually in the tank. The measurements are real. Maybe it's not me who's wrong." The conference moved on to other presentations, but the doubt lingered. The whispers in hallways. The conversations at dinner. Davidson's folly, some called it. An old man wasting the prime years of his career counting invisible atoms in a hole in the ground, producing results that made no sense, refusing to admit that maybe, just maybe, his experiment was flawed. But Davis kept going. Day after day, year after year, he descended into the mine. He monitored the tank. He ran extraction cycles. He counted atoms. He published papers. He presented at conferences. He answered the same skeptical questions over and over. Margaret supported him as best she could, but the strain was visible. The years in South Dakota, the isolation, the professional criticism, the financial uncertainty. This is substantial information, and processing it takes effort. That effort is worth it. The pattern you're seeing, one man's determination against a tide of doubt, is central to understanding how science actually works. Not eureka moments, but decades of patient work. The years became a decade. The decade stretched toward 2. In 1989, Margaret Davis died of cancer. She was 68 years old. Raymond was in the middle of an extraction cycle when he got the call from the hospital. The argon was being purified. The procedure was at a critical stage. If he left, weeks of work would be lost. He stayed in the mine and finished the extraction. He missed her funeral. His daughter never quite forgave him for that. She understood intellectually that the experiment required constant attention, that interrupting the process would compromise the data. But understanding and forgiving are different things. Davis visited Margaret's grave a week later. He stood there alone, his hand on the headstone, and tried to explain. "I'm sorry," he said to the stone. "I'm sorry I wasn't there, but I was right, Margaret. I know I was right. The measurements are real. Something is happening to those neutrinos. I just have to wait long enough for someone to figure out what." By 1990, Davis was 72 years old. He had been running the homestake experiment for 26 years. More than a quarter century of his life spent descending into a mine counting atoms, defending his results against skepticism. Most of his colleagues had retired. Some had died. The field had moved on to other questions, other experiments. But Davis kept running the detector. Every few weeks, another extraction cycle, another handful of atoms, another data point showing the same deficit. 1/3, always 1/3. Younger physicists sometimes asked him why he continued. Why not shut down the experiment? Why not admit that maybe the measurements were wrong? Davis would just shake his head. "The books must balance," he would say. "Energy is conserved. The neutrinos are being produced. They're arriving here. I'm detecting some of them. If I'm only seeing 1/3, that means 2/3 are doing something I can't detect. Something is happening to them. Someone will figure out what. I just have to keep measuring until they do." On Christmas Eve 1990, Davis was alone in the mine. His family had stopped expecting him to be present for holidays. The mine was quiet. The detector sat in its cavern, a monument to stubbornness. He placed his hand on the tank, feeling the cold metal, thinking about all the neutrinos passing through it at that very moment. 65 billion per second per square centimeter. Trillions streaming through the tank. And occasionally, so rarely it defied imagination, one would strike a chlorine nucleus. "I'm touching the sun," he said quietly to the empty cavern. "How can I stop?" Across the Pacific Ocean, in the mountains of Japan's Gifu Prefecture, another physicist was building something extraordinary. His name was Takaaki Kajita Nakamura. He was young, ambitious, brilliant, and convinced that the solar neutrino problem could be solved with a different approach. In the early 1990s, Kajita Nakamura was working on a detector called Super Kamiokande, located deep inside the Mozumi mine, about 250 kilometers northwest of Tokyo beneath Mount Ikino. Super Kamiokande represented a dramatic leap in scale and sensitivity compared to anything that had come before. The detector was a cylindrical stainless steel tank about 40 meters in diameter and 40 meters tall. Imagine a building 12 stories high and as wide as a city block, except instead of floors and rooms, it's a single enormous tank, filled with 50,000 metric tons of ultra-pure water. The water was so pure that it had been filtered to remove virtually every trace of dissolved minerals and contaminants. Even tiny impurities could produce spurious light signals that would mask the faint neutrino events they were trying to detect. The water was cleaner than anything you've ever drunk. Cleaner than distilled water. Cleaner than water used in the most sensitive medical procedures. Surrounding the water on all sides were 11,180 photomultiplier tubes. Extraordinarily sensitive light detectors, each about 50 centimeters in diameter, mounted on the inner walls of the tank like an army of unblinking eyes. These photomultiplier tubes were so sensitive that they could detect a single photon of light, a single quantum of electromagnetic energy. They stared inward at the water from every direction, watching, waiting for the faintest flash. The detection principle relied on a phenomenon called Cherenkov radiation. When a charged particle travels through water faster than the speed of light in water, which is about 75% of the speed of light in vacuum, it creates a cone of faint blue light. This is the optical equivalent of a sonic boom. A jet traveling faster than the speed of sound in air creates a shock wave, a cone of compressed air that we hear as a thunderous boom. Similarly, a particle traveling faster than the local speed of light in a transparent medium creates a shock wave of light, a cone of photons spreading out behind it. No law of physics is violated. Nothing is exceeding the speed of light in a vacuum. But light travels slower in water than in vacuum, and a high-energy charged particle can exceed that reduced speed. When a neutrino interacts with a water molecule through the weak force, an event that happens only a handful of times per day, even in 50,000 tons of water, it can produce a charged particle, either an electron or a muon, depending on the neutrino's flavor. If that charged particle is fast enough, it emits a cone of Cherenkov light. The photomultiplier tubes detect this faint ring of light, and from the pattern, the shape of the ring, its brightness, its sharpness, its position on the detector walls, physicists can reconstruct the direction the neutrino came from, its energy, and crucially, its flavor. Kajita Nakamura wasn't primarily focused on solar neutrinos, at least not at first. He was studying atmospheric neutrinos. These are neutrinos produced when cosmic rays from deep space strike atoms in Earth's upper atmosphere. Cosmic rays are mostly high-energy protons traveling at very nearly the speed of light, originating from supernovae, active galactic nuclei, and other violent astrophysical events. They constantly bombard Earth's atmosphere, have been doing so for billions of years, will continue doing so for billions more. When these fast-moving particles slam into nitrogen and oxygen molecules in the upper atmosphere at altitudes of roughly 15 to 35 kilometers, they create cascading showers of secondary particles. Among these are pions, unstable particles that quickly decay, and many of their decay products include neutrinos, specifically muon neutrinos. These atmospheric neutrinos rain down on Earth continuously from every direction in the sky. Some travel downward through just a few dozen kilometers of atmosphere to reach detectors on or near the surface. A short journey, 50 kilometers maybe. Others are produced on the far side of the planet, travel downward through the atmosphere. They are then passed through the entire Earth, all 12,700 kilometers of rock and iron and mantle, and arrive at the detector from below. The journey from above may be 50 kilometers through air. The journey from below up to 12,700 kilometers through solid planet. If neutrinos don't oscillate, if they don't change flavor during flight, both groups should arrive in equal numbers. The production rate is essentially the same in all directions. The cosmic ray flux is roughly uniform across the sky. The neutrinos coming from below travel a longer distance through the Earth, but neutrinos pass through the Earth without difficulty, so that shouldn't matter. Both groups should look the same, but they didn't. In June of 1998, Takaaki Kajita Nakamura stood before an audience of physicists at a conference in Takayama, Japan. The conference room was packed. Word had spread that Super Kamiokande had something significant to announce. Physicists from around the world had come to hear it. Kajita Nakamura was 39 years old. He had spent the last decade of his life working on this experiment, overseeing construction, calibrating detectors, analyzing data. He presented slides showing event rates for atmospheric neutrinos arriving from different directions. The data was clear. The number of muon neutrinos arriving from below after traveling through the Earth was significantly less than the number arriving from above. Not a small difference, not a subtle effect, a clear, obvious deficit. The downward traveling neutrinos, which had only traveled a few dozen kilometers through atmosphere, arrived at nearly the expected rate. The upward traveling neutrinos, which had traveled thousands of kilometers through the planet, showed a deficit that increased with distance. The farther the neutrinos had traveled, the more of them had disappeared. Kajita Nakamura's voice was calm, methodical as he explained the implications. He had rehearsed this presentation dozens of times. He knew every slide, every number, every objection that might be raised. The deficit depends on distance traveled, he said, in exactly the way oscillation theory predicts. Muon neutrinos that travel longer distances have more time to oscillate into tau neutrinos, which our detection method cannot easily identify. The tau neutrino can interact with water, but it produces a tau lepton, which is too heavy and short-lived to create a clear Cherenkov ring. We can't see them easily. So they appear to us as missing. He clicked to the next slide. Muon neutrinos that travel only a short distance don't have enough time to oscillate significantly, so they arrive as muon neutrinos and are detected normally. The pattern matches oscillation predictions across every distance range we can measure. He paused and looked directly at the audience. This is direct evidence that neutrinos change flavor as they travel through space. And because flavor oscillation requires the three neutrino types to have different masses, it means neutrinos have mass. The standard model, which assumes massless neutrinos, must be updated. The room erupted. Questions, arguments, demands for more data, requests for clarification on systematic uncertainties. But Kajita Nakamura had the data. Years of it. Thousands of events. The pattern was undeniable. Neutrinos were oscillating, changing from one flavor to another during flight, like a particle wearing different mass, swapping identities as it traveled. And this meant something profound. If neutrinos have mass, even a tiny amount, it meant the standard model of particle physics, the framework that had been constructed over decades to describe all known particles and forces, was incomplete. It needed to be revised, updated. expanded. A fundamental assumption had been wrong. And suddenly, Raymond Aldrich Davis's 3 decades of anomalous measurements made sense. Meanwhile, in Canada, another experiment was reaching completion. Arthur B. MacDonald Thornhill, a Canadian physicist with a talent for elegant experimental design and a reputation for meticulous attention to systematic uncertainties, was leading the Sudbury Neutrino Observatory, known as SNO. SNO was located about 2,000 meters underground in an active nickel mine near Sudbury, Ontario. The mine had been in operation for decades, extracting nickel and other valuable minerals from the ancient rock of the Canadian Shield. But now, deep in its tunnels, physicists were installing something unprecedented. The heart of the detector contained 1,000 metric tons of heavy water. Water in which the ordinary hydrogen atoms, which have one proton and no neutrons in their nucleus, are replaced by deuterium, a heavier isotope of hydrogen whose nucleus contains one proton and one neutron. This heavy water was extraordinarily valuable. It had been borrowed from Canada's nuclear industry, which uses heavy water as a moderator in CANDU reactors. The total value was roughly 30 million Canadian dollars. It was kept in a 12-meter diameter acrylic vessel, a clear sphere suspended in the center of a larger cavity filled with ordinary ultra-pure water. Surrounding this entire assembly were about 9,600 photomultiplier tubes watching for flashes of Cherenkov light. Heavy water gave SNO a unique capability that no previous detector possessed. It could detect neutrinos through 3 different interaction channels, each with different sensitivities to neutrino flavor. The first was the charged current reaction. In this process, an electron neutrino interacts with the deuterium nucleus and transforms it into 2 protons plus an electron. The electron flies out at high speed, creating Cherenkov light. This reaction is sensitive only to electron neutrinos. Muon and tau neutrinos cannot trigger it because they would produce muons, or tau leptons, and the energy threshold is wrong. The second was the neutral current reaction. In this process, a neutrino of any flavor, electron, muon, or tau, interacts with the deuterium nucleus and breaks it apart into a free proton and a free neutron. The neutrino bounces off elastically and continues on its way. The free neutron bounces around for a few microseconds before being captured by another nucleus, producing a detectable gamma ray. This reaction is equally sensitive to all 3 flavors. It doesn't care what flavor the neutrino is. It just counts total neutrinos. The third was elastic scattering, where a neutrino bounces off an electron. This is sensitive to all flavors, but predominantly to electron neutrinos because of the way the weak force couples to different particles. The logic was devastatingly simple and elegant. If the solar neutrino problem was caused by incorrect solar models, if the sun really was producing fewer neutrinos than predicted, then both the charged current measurement and the neutral current measurement would show a deficit. Fewer total neutrinos being produced means fewer electron neutrinos and fewer total neutrinos arriving. Both channels would see the deficit. But if the problem was caused by neutrino oscillation, if electron neutrinos were changing into muon and tau neutrinos during their 8-minute journey from the sun's core to Earth, then the charged current measurement would show a deficit because it only sees electron neutrinos, and some of them have transformed into other flavors by the time they arrive. But the neutral current measurement would show the full expected rate because it counts all flavors equally. The total number of neutrinos hasn't changed. They've just changed flavor. They're all still arriving. They're just wearing different masks. MacDonald Thornhill and his international team spent years carefully calibrating the detector, measuring backgrounds, understanding systematic uncertainties, accumulating data with a painstaking care. Every aspect of the experiment was checked and double-checked. The purity of the heavy water, the response of the photomultiplier tubes, the reconstruction algorithms that turned patterns of light into neutrino energies and directions, the background from radioactive contaminants in the detector materials, the cosmic ray muons that occasionally made it through the 2 kilometers of rock overhead. Everything had to be understood with extraordinary precision because the stakes were so high. And then in June of 2001, they were ready to announce their results. You're processing a complex chain of logic here. Solar models predict X neutrinos. Davis sees X divided by 3. Either the sun is wrong or the neutrinos are changing. Kajita Nakamura shows neutrinos change with distance. MacDonald Thornhill is about to prove all the neutrinos are accounted for. Hold that progression in your mind. The presentation was made at a physics conference in Vancouver, Canada. MacDonald Thornhill stood at the podium, slides projected on the screen behind him. The room was full. This was the moment the neutrino physics community had been waiting for. He showed the charged current measurement first. approximately 34% of the expected electron-neutrino rate. The number appeared on the screen, 34%, with small error bars indicating high statistical precision. This was consistent with what Raymond Aldrich Davis had been measuring for 3 decades in the Homestake mine. The deficit was real, electron neutrinos were missing. Davis had been right all along about what he was seeing. The skeptics who had questioned his counting methods, his extraction efficiency, his competence, had been wrong. Then McDonald Thornhill showed the neutral current measurement, 100% of the expected total neutrino rate. The number appeared, 100%. Within experimental uncertainties, a perfect match to solar model predictions. The room went silent. People in the audience were doing the calculation in their heads. If you're only seeing 34% electron neutrinos, but 100% total neutrinos, that means the other 66% are arriving as muon and tau neutrinos. They changed flavor. They oscillated. McDonald Thornhill let the data speak for itself for a moment. He looked out at the audience, seeing the realizations spreading across faces. Then he said quietly but clearly, his voice carrying to every corner of the room, "Every neutrino the sun produces is arriving at Earth. None are missing. None have disappeared. The deficit that Dr. Raymond Davis has been measuring faithfully for more than 30 years is entirely explained by flavor transformation. The neutrinos change identity during their journey from the sun to Earth. The standard model assumption that neutrinos are massless is incorrect. They have mass, and they oscillate. The solar neutrino problem, which had haunted physics for 32 years, which had consumed the career of Raymond Aldrich Davis, which had spawned thousands of papers and countless hours of debate, was solved, and the resolution was beautiful in its completeness. The sun was working exactly as models predicted. The nuclear fusion reactions in the core were producing neutrinos at exactly the predicted rate. The nuclear physics was correct. The solar models were correct. Raymond Aldrich Davis's experiment was correct. His extraction methods were correct. His counting was correct. His measurements had been accurate all along. Everyone had been right except for the one assumption that everyone had taken for granted, that neutrinos were massless and couldn't change flavor. The neutrinos were all there, every single one the sun had produced, every single one predicted by the solar models. They had simply changed flavor on the way to Earth, converting from electron neutrinos, the only type Davis's chlorine detector could see, into muon and tau neutrinos that his experiment was blind to. They hadn't disappeared, they had disguised themselves. And this oscillation proved beyond any doubt that neutrinos have mass. Because the mathematics of quantum mechanics is absolutely clear, massless particles cannot oscillate between different flavors. Only particles with mass can do that. And furthermore, the 3 flavors must have different masses for oscillation to occur. The standard model had to be updated. A new chapter had to be written. The neutrino, which had been assumed to be massless since Pauli Brenner first proposed it in 1930, had mass after all. Take a breath here. You've just witnessed the resolution of a 3-decade mystery. Raymond Aldrich Davis counted atoms in darkness for 32 years while colleagues doubted him. And he was right. The universe was simply more subtle than anyone expected. The neutrinos were playing a trick nobody anticipated. Raymond Aldrich Davis, who had spent 32 years being told his results were wrong, who had been called stubborn, obsessive, unable to admit error, was vindicated. The data had been right from the beginning. It was the assumptions about neutrinos that had been wrong. The Nobel Prize in Physics for 2002 was awarded jointly to Raymond Aldrich Davis and Masatoshi Koshiba Yamamoto, who had built the Kamiokande detector in Japan, the predecessor to Super Kamiokande, and had confirmed the solar neutrino deficit using a completely different detection method based on Cherenkov radiation. Davis was 84 years old when he received the call from Stockholm. He was in his study at home. He hadn't descended into the Homestake mine in several years. The detector had been decommissioned. The tank drained, the mine sealed. His decades-long vigil was over. The phone rang early in the morning. He picked it up, expecting a call from one of his children. Instead, he heard a heavily accented voice speaking English with careful precision. "Dr. Davis, this is the Royal Swedish Academy of Sciences. We are pleased to inform you that you have been awarded the Nobel Prize in Physics for your pioneering contributions to astrophysics, in particular for the detection of cosmic neutrinos." Davis sat down slowly in his chair. His hands were shaking. He was 84 years old. His wife, Margaret, had been dead for 13 years. Most of his colleagues from the early days had retired or died. He had spent 38 years, more than half his professional life, pursuing neutrinos. First learning the techniques, then building the detector, then running it, then defending it against skepticism, then watching as younger physicists with newer detectors figured out what was actually happening. "Thank you," he said quietly into the phone. "Thank you." That December in Stockholm, Raymond Aldrich Davis stood before the audience at the Nobel Prize ceremony. He was frail now, his hair white, his movements slow. But his voice when he spoke was steady. He delivered his acceptance speech with the same precision he had brought to counting atoms. 38 years ago, he said, I descended into a mine in South Dakota with what most people considered an improbable idea, to catch particles from the sun that had never been directly detected before. Particles that passed through the entire Earth without even noticing. He paused, letting the words settle. Today, neutrinos have shown us the sun's heart in the final breath of dying stars. They've taught us that our models of the sun were correct and that our assumptions about neutrinos were not. They've shown us that the universe is more subtle, more beautiful, more surprising than we imagined. His eyes scanned the audience, seeing faces young and old, physicists who had devoted their lives to understanding nature. "And I have one question left," he said. "What will they show us next?" The audience applauded warmly. Davis nodded in acknowledgement, but he wasn't finished. "Because the universe is screaming at us in neutrinos," he continued. "We've only just learned to listen. We've built bigger detectors. We've developed new techniques. We've proven that neutrinos oscillate and have mass. But there are still questions. What is that mass exactly? Are neutrinos their own antiparticles? Do they hold the secret to why matter exists instead of antimatter?" He paused again. "Imagine what we'll hear with bigger ears. Imagine what the next generation will discover." The applause was thunderous. Davis stepped back from the podium, the gold medal heavy around his neck, and thought about Margaret, who had supported him through the long years of doubt and isolation. He wished she could have seen this moment. He wished she could have known that the patience had been worth it. 3 months later, in May of 2003, Raymond Aldrich Davis died peacefully at the age of 85. On the day before he died, he asked his daughter to drive him past the entrance to the Homestake mine. She wheeled him to the gate in his wheelchair. The mine had been closed for years. The entrance was sealed, but he sat there for a long time looking at it. 615 tons, he said quietly, 1.47 kilometers down. 32 years. I touched the sun, you know. Every atom I counted came from fusion reactions in the sun's core. I touched the sun. His daughter didn't understand, not really, but she put her hand on his shoulder and sat with him until he was ready to leave. But the story of neutrinos didn't end with the solution to the solar neutrino problem. Because even before the puzzle was solved, the universe had sent another message. A message that demonstrated the power of neutrinos as messengers from the cosmos. It happened on February 23, 1987. While Raymond Aldrich Davis was still running his experiment in the Homestake mine, still accumulating data, still being questioned by skeptics, still defending his one-third measurement, something extraordinary occurred in a galaxy 168,000 light-years away. A blue supergiant star in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, visible from the southern hemisphere, reached the end of its life. The star, cataloged with the unromantic designation Sandalik, -69 degrees 202, had been burning through its nuclear fuel for roughly 20 million years. It had fused hydrogen into helium in its core for most of that time, releasing energy shining steadily in the night sky of the Large Magellanic Cloud. But hydrogen doesn't last forever. Eventually, the core ran out of hydrogen fuel. It contracted and heated up. The temperature and pressure rose until helium could fuse into carbon. The star adjusted, swelled, and continued shining. Then the helium ran out. Carbon fused into neon, neon into oxygen, oxygen into silicon, each stage shorter than the last, each burning at higher temperatures and pressures. The star was racing toward an inevitable conclusion. Finally, silicon fused into iron, and iron is where the road ends. Iron is the most stable nucleus. Fusing iron into heavier elements doesn't release energy. It consumes energy. The stellar core, now made of iron, could no longer support itself against gravity through fusion reactions. In a fraction of a second, the core collapsed. What happened next released more energy than most people can meaningfully comprehend. The core, roughly the mass of our sun, but compressed into a region only a few thousand kilometers across, imploded. It collapsed from the size of a small planet to a sphere roughly 30 kilometers in diameter. A neutron star was born in less than 1 second. The gravitational potential energy released by this collapse was approximately 3 × 10⁻46 joules. That is more energy than our sun will produce in its entire 10 billion year lifetime, released in seconds. And roughly 99% of that energy, not half, not most, but virtually all of it, was carried away by neutrinos. The visible explosion, the shockwave that tore the star apart and sent its outer layers flying into space at thousands of kilometers per second. The brilliant flash of light that would soon be visible to telescopes across the southern hemisphere. All of that spectacular display was powered by the remaining 1% of the energy. The other 99% left in the form of neutrinos. The neutrinos escaped first. They had to. The collapsing core produced a flood of neutrinos of all flavors in unimaginable quantities. Roughly 10 to the 58th neutrinos were released in a burst lasting about 10 seconds. Write that number out: 100 million trillion 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 neutrinos. These neutrinos streamed outward from the core at nearly the speed of light, passing through the outer layers of the dying star, through hundreds of thousands of kilometers of stellar material, as if those layers were empty space. The light, by contrast, had to wait. The shock wave generated by the core bounced the rebound of infalling matter off the newly formed neutron star, had to fight its way outward through the star's massive envelope. It took hours for the shock wave to reach the surface and break through. Only then did the star begin to brighten visibly, but the neutrinos were already gone, already crossing intergalactic space, already halfway to the Milky Way. 3 neutrino detectors on Earth registered the event. Kamiokande 2 in Japan, the predecessor to Super Kamiokande, detected 12 neutrinos over a span of about 13 seconds. Each one triggered a flash of Cherenkov light in the detector's 3,000 tons of water. Each one left a distinctive ring pattern on the walls of photomultiplier tubes. The Irvine, Michigan Brookhaven detector in a salt mine in Ohio detected 8 neutrinos in roughly the same time window. The Baksan Neutrino Observatory in the Caucasus Mountains of Russia detected 25 neutrinos in total, captured within a window of roughly 13 seconds. That's all. 25 particles from an event that released 10 to the 58th of them. But consider what those 25 neutrinos represent. They traveled 168,000 light-years across intergalactic space from a galaxy beyond our own. The distance is roughly 1.59 times 10 to the 18th kilometers. They crossed the void between galaxies, a region so empty that you might encounter only 1 atom per cubic meter. They arrived at Earth and passed through the planet's entire mass, 12,700 kilometers of rock and iron and mantle, continuing through as if the Earth were made of nothing but vacuum. Out of the uncountable trillions that passed through each detector, a handful, just a handful, happened by pure statistical chance to interact with atoms in the water or the detector medium. The probability of any individual neutrino interacting was absurdly small, the same 10 to the negative 44th square centimeters we calculated earlier. But the sheer number of neutrinos from the supernova was so staggeringly large that a few interactions were statistically inevitable. And those 25 neutrinos arrived approximately 3 hours before the first visible light from the supernova was observed by optical astronomers in the southern hemisphere. 3 hours. Think about that. The neutrinos carried news of the core collapse while the shock wave was still fighting its way through the star's outer layers, while the surface was still intact, while the star still looked to any telescope like an ordinary blue supergiant. By the time telescopes spotted the brightening star, by the time Ian Shelton at Las Campanas Observatory in Chile developed his photographic plate and noticed a new bright star, where none had been the night before, the neutrinos had already told physicists on Earth exactly what had happened. A star had died, its core had collapsed, a neutron star had formed. An explosion was propagating outward. The neutrinos were the heralds, the advanced messengers of stellar death. Masatoshi Koshiba Yamamoto was 61 years old in February of 1987. He had been running the Kamiokande detector for several years, primarily looking for proton decay, a hypothetical process that the simplest grand unified theories predicted, but that had never been observed. The detector hadn't found proton decay, but it had proven exquisitely sensitive to neutrinos. On the morning of February 23rd, Koshiba Yamamoto was reviewing data from the previous night's operation when he noticed something unusual. 12 neutrino events, all within a 13-second window, all coming from roughly the same direction in the sky. This was unprecedented. Normally, the detector saw maybe 1 or 2 neutrino events per day from atmospheric neutrinos. 12 in 13 seconds was extraordinary. His first thought was instrumental error. Some malfunction in the electronics, some noise in the system. But the events looked clean. Each one had the characteristic signature of a neutrino interaction, a clear ring of Cherenkov light indicating a particle traveling faster than light speed in water, originating from a single point. He called colleagues. He checked logs. He verified that the detector had been operating normally. Then he started calling other neutrino detectors around the world. Had they seen anything? The IMB detector in Ohio had seen 8 events in the same time window, from the same direction. Baksan in Russia had seen 5. Different detectors, different hemispheres, different detection technologies, all seeing a burst of neutrinos from the same direction at the same time. Koshiba Yamamoto looked at a star map. The direction the neutrinos had come from pointed toward the Large Magellanic Cloud. 3 hours later, the first reports of a visible supernova started coming in from optical astronomers in the Southern Hemisphere. Supernova 1987. The first naked-eye supernova visible from Earth since Kepler's supernova in 1604, 383 years earlier. Koshiba Yamamoto sat in his office, looking at the neutrino data and the optical reports, and understood what had happened. "We heard the stars scream," he said quietly to a colleague, "and we understood the language." The detection of neutrinos from supernova, 1987 was a triumph of both theory and experiment. For decades, astrophysicists had built detailed models of how massive stars die. The models predicted that the core would collapse when it could no longer generate energy through fusion. They predicted that a neutron star would form. They predicted that an enormous burst of neutrinos would carry away the vast majority of the gravitational binding energy released by the collapse. They predicted that a shockwave would follow, powered by a tiny fraction of that energy, producing the visible explosion. The 25 neutrinos from supernova, 1987 confirmed this picture with stunning directness. The energies of the detected neutrinos matched theoretical predictions. They were in the range of a few tens of millions of electron volts, exactly what models said neutrinos from a collapsing stellar core should have. The duration of the burst, about 13 seconds, matched the expected timescale of neutron star formation and early cooling. The core collapses in a fraction of a second, but the newly formed neutron star continues radiating neutrinos for several seconds as it cools from billions of degrees down to millions. The total energy implied by scaling up from 25 detected neutrinos to the full flux accounting for the distance and the small size of the detectors was consistent with the predicted 3 × 10 to the 46 joules. Everything fit, every prediction was confirmed. The models of how stars die were correct, and neutrinos had proven it. More than that, the neutrinos had arrived first. They had announced the death of the star 3 hours before light did. This demonstrated something profound about neutrinos as astronomical messengers. For most of human history, astronomy was done exclusively with light, visible light from the earliest stargazers looking up at the night sky. Radio waves starting in the 1930s. Infrared, ultraviolet X-rays, gamma rays as technology advanced through the 20th century. Every telescope ever built, from Galileo's simple refractor to the Hubble Space Telescope to the James Webb Space Telescope, detects some form of electromagnetic radiation. And light has taught us an extraordinary amount about the universe. Our entire picture of the cosmos, from the planets in our solar system to the most distant galaxies at the edge of the observable universe, has been built from photons. But light has limitations. Photons interact electromagnetically. That's how we detect them, but it's also why they get blocked, absorbed, scattered, and distorted by matter between the source and the observer. Dense clouds of gas and dust obscure our view of the galactic center. We can't see the core of our own galaxy in visible light because there's too much stuff in the way. The interiors of stars are completely opaque to light. Photons produced by fusion in the sun's core take 170,000 years to random walk to the surface. The early universe, before about 380,000 years after the Big Bang, was an opaque plasma. Photons couldn't travel freely. They were constantly scattered by free electrons. The cosmic microwave background, the earliest light we can see, comes from the moment when the universe cooled enough for atoms to form and photons to travel freely. But we can't see earlier than that with light. There are entire realms of the cosmos that light simply cannot show us. Neutrinos have no such limitation. Because they interact only through the weak force, because they have no electric charge, because they feel neither electromagnetism nor the strong force, the matter that blocks light is utterly transparent to them. Neutrinos stream directly out of the cores of stars. They pass through hundreds of thousands of kilometers of stellar plasma in seconds. They carry information directly from the nuclear furnace at the center. They emerge from supernovae hours before the light, carrying information about the core collapse, that photons trapped in the expanding debris cannot yet reveal. They could, in principle, show us the universe as it was earlier than 380,000 years after the Big Bang. The cosmic neutrino background, if we could detect it, would show us the universe at 1 second old. Neutrinos see through everything, and that makes them perfect messengers from the deepest, darkest, most violent places in the universe. Masatoshi Koshiba Yamamoto shared the 2002 Nobel Prize in Physics with Raymond Aldrich Davis. The citation specifically mentioned the detection of cosmic neutrinos, including the neutrinos from supernova 1987A. It was a recognition not just of a single measurement, but of the birth of neutrino astronomy. A new window on the universe had opened. But to look through that window at the most distant and violent objects in the cosmos to catch neutrinos from black holes and colliding galaxies, physicists would need to build something unprecedented, something enormous, something extreme. They would need to build a detector the size of a mountain in the most inhospitable place on Earth, in Antarctica, in ice. The next part of this journey will show you how far the search for neutrinos has taken us. You've seen patience in the form of Raymond Davis. You're about to see ambition on a scale that's hard to fathom. You're ready. In November of 2005, a woman stepped off a military transport aircraft onto the frozen plateau at the geographic South Pole. Dr. Elena Castellano was 42 years old, Italian-American, a particle physicist who had spent the previous decade advocating for something that most of her colleagues considered either visionary or completely insane, depending on who you asked and what mood they were in. She wanted to turn 1 cubic kilometer of Antarctic ice into a neutrino detector. 1 cubic kilometer, 1 billion cubic meters, 1 trillion liters, the largest scientific instrument ever built. The temperature at the Amundsen-Scott South Pole Station when Elena arrived was negative 40 degrees Fahrenheit. The wind was light, fortunately. At negative 40, even a modest wind can be dangerous. The sun was above the horizon. It wouldn't set for another 3 months. This was the Antarctic summer, the only time of year when major construction work was possible, when supply flights could land regularly when the temperature occasionally briefly rose above zero. A tall man with a weathered face and a Belgian accent approached her across the ice. His name was Francis Halzen. He was 62 years old, a professor at the University of Wisconsin, and the principal investigator of the IceCube project. The man whose vision, persistence, and ability to convince funding agencies had made this audacious project possible. "Welcome to the bottom of the world, Elena," he said, extending a gloved hand. "Want to drill to hell?" Elena shook his hand and looked out across the endless white expanse. The plateau stretched to the horizon in every direction. Flat, featureless, white. The sky was a pale blue, the sun a cold disk that circled the horizon without setting. "Let's catch some ghosts from the edge of the universe," she said. The IceCube Neutrino Observatory was unprecedented in every dimension. The plan was to drill 86 holes into the Antarctic ice sheet using hot water drills. Each hole would go down between 1,450 and 2,450 meters, nearly 1.5 miles down into ice. Into each hole, they would lower a cable called a string containing 60 digital optical modules. These were basketball-sized glass spheres, each containing a 10-inch photomultiplier tube and associated electronics. The electronics included amplifiers, digitizers, processors, and communication systems, all designed to survive, being frozen into ice at negative 50 degrees Celsius for at least a decade. 86 strings, 60 sensors per string, 5,160 optical modules total, distributed throughout a cubic kilometer of ice, a cube about 1,000 meters on each side, instrumented to detect the faint flashes of Cherenkov light produced when high-energy neutrinos occasionally interacted with atoms in the ice. The ice at these depths, compressed under the weight of nearly 2.5 kilometers of ice above it, squeezed over hundreds of thousands of years, was extraordinarily transparent. It was clearer than any glass humans can manufacture. Photons of visible light, particularly blue light, which is what Cherenkov radiation produces, could travel over 100 meters through this ice before being absorbed. When a neutrino with sufficient energy interacted with an atom in the ice with an oxygen nucleus or a hydrogen nucleus in a frozen water molecule, the interaction would produce a charged particle, either an electron, a muon, or a tau lepton, depending on the neutrino's flavor and the type of interaction. If that charged particle had enough energy, it would travel through the ice faster than the speed of light in ice, producing a cone of Cherenkov light. The optical modules would detect this light, and from the pattern from which sensors were triggered, and in what order and with what intensity, from the timing with nanosecond precision, physicists could reconstruct the energy and direction of the original neutrino. IceCube wasn't designed to detect solar neutrinos. Those energies were far too low. The detector wasn't sensitive to neutrinos with energies in the millions of electron volts. The threshold was much higher. IceCube was built to detect neutrinos at energies that no terrestrial particle accelerator could produce. Neutrinos with energies in the billions of electron volts, the tera-electron volt range. And beyond that into the peta-electron volt range. Quadrillions of electron volts. These are neutrinos produced not by fusion in stellar cores, but by the most violent processes in the universe. Supermassive black holes devouring matter. Jets of particles accelerated to 99.99% of the speed of light. Gamma-ray bursts from collapsing stars, colliding galaxies. The construction was a nightmare. Hot water drills, essentially enormous high-pressure hoses that melted holes through the ice, failed regularly in the brutal cold. The drill tower, a massive steel structure that had to be erected each drilling season, groaned and swayed in the wind. Cables froze during deployment. Optical sensors cracked under the pressure of being lowered into kilometer-deep holes. Supply flights from McMurdo Station, the main U.S. base on the Antarctic coast, were frequently canceled by weather. The South Pole Station ran on carefully managed supplies. Everything had to be planned months in advance. A broken drill bit could halt construction for weeks while a replacement was flown in, if weather permitted. Team members suffered frostbite despite precautions. The psychological strain of isolation of spending months in one of the most remote places on Earth, where the sun either never sets or never rises depending on the season, affected everyone differently. Some people thrived, others broke down and had to be sent back to civilization. Elena Castellano spent 5 Antarctic summers overseeing construction. November through February, 5 years in a row at the South Pole. Each summer was a frantic race to drill as many holes and deploy as many strings as possible before the weather turned and the station entered winter mode. The rest of the year, she was back at the University of California, Berkeley, analyzing data, writing papers, attending conferences, fighting for continued funding, training graduate students. She missed her daughter Lily's 10th birthday in 2007. She was on the ice supervising a critical string deployment. Communication was limited. She managed a satellite phone call. Lily understood, or said she did. Her marriage fell apart. The divorce was finalized in 2009 while Elena was in Antarctica. Her ex-husband had tried to make it work, tried to accept that his wife spent half of every year at the bottom of the world chasing invisible particles. But eventually he'd had enough. His last words to her before the divorce was final: "You love that ice more than you love us." Elena never answered that accusation directly. But late at night, alone in her room at the South Pole Station, staring at construction schedules and detector diagrams, she wondered if he was right. What drove her wasn't love of ice. It was an obsession with a place. It was the knowledge that somewhere out there, 4 billion light years away, maybe 10 billion light years away, maybe at the very edge of the observable universe, black holes were devouring stars. Galaxies were colliding. Jets of matter were being shot across intergalactic space at nearly the speed of light. And those events were screaming in neutrinos. Messages from the most violent places in the cosmos, traveling across unimaginable distances, passing through entire galaxies without slowing down, arriving at Earth by the billions every second. And almost no one was listening. IceCube would listen. Marcus Delroy, the chief engineer, a 45-year-old former Navy submariner who had spent years under Arctic ice in nuclear submarines and knew cold and isolation better than most people, became Elena's anchor. Her voice of sanity when the pressure threatened to overwhelm her. One night after a particularly difficult day, when a drill had broken and set them back 2 weeks, Marcus found Elena in the data center staring at simulations. "Ma'am," he said, "I've been under Arctic ice in a tin can with 100 other men breathing recycled air for months at a time. At least here we can see the stars. At least here we're building something that will last." Elena looked at him and managed a tired smile. "Thank you, Marcus. I needed to hear that. This section carries substantial emotional weight because it's about human cost, the sacrifice required to push science forward." Raymond Davis gave 32 years and his wife's funeral. Elena Castellano gave her marriage and her daughter's childhood. Hold that in your mind alongside the discoveries. Nothing comes free. In May of 2011, the 86th and final string was deployed into the ice. The last hole was drilled, the cable carefully lowered the ice, allowed to refreeze around it, sealing the sensors permanently in place. IceCube was complete. 1 cubic kilometer of instrumented ice. The largest neutrino detector ever built and likely to remain the largest for decades. Sitting at the geographic South Pole, embedded in ice 2.5 kilometers below the surface, listening to the universe with 5,000 electronic ears. But completion of construction didn't mean instant results. The detector entered a calibration period. Physicists had to teach it to distinguish real neutrino events from background noise. Cosmic ray muons, produced when cosmic rays hit the atmosphere above the South Pole, rained down constantly. These muons could penetrate deep into the ice. They had to be identified and filtered out. The collaboration developed sophisticated algorithms to reconstruct particle directions. Upgoing events particles coming up through the Earth were almost certainly neutrinos, because neutrinos are the only particles that can pass through the entire planet. Downgoing events were mostly cosmic ray muons. Months passed, the detector ran continuously accumulating data, but the early results were dominated by background. Team morale began to drop. Physicists who had spent years, in some cases a decade, building this enormous instrument were starting to wonder if they would ever see a clear cosmic neutrino signal. Some of the graduate students who had joined the collaboration as first-year students were now finishing their PhDs. Their entire doctoral careers had been spent building and calibrating the detector. They needed results. They needed to graduate. They needed something to show for all the years of work. Elena instituted what she called Movie Mondays. Every Monday evening, the team at the South Pole would gather in the common room and watch science fiction films. Classic movies like 2001, A Space Odyssey, Contact Interstellar. Anything to maintain team cohesion, to remind people why they were doing this, to keep morale from collapsing entirely. Marcus, who had seen his share of morale crises in submarine service, joked during one screening of The Abyss, a film about deep-sea exploration. At least they had water pressure trying to crush them. We just have cold and boredom. People laughed, but the concern was real. The detector was working. The electronics were stable. The ice was as transparent as predicted. The optical modules were triggering on events. Everything technical was functioning correctly. But where were the cosmic neutrinos? Then in April of 2013, two events appeared in the data that were unlike anything the collaboration had seen before. Both had energies exceeding 1 peta-electron volt, 1 quadrillion electron volts. That's roughly 1 million times higher than any neutrino that had ever been produced by a particle accelerator on Earth. The Large Hadron Collider, the most powerful accelerator ever built, can't produce neutrinos at these energies. These neutrinos had to come from space, from astrophysical sources. The team ran every possible check. Could these be cosmic ray muons, somehow misreconstructed numb? The energies were too high, far higher than muons from atmospheric cosmic rays typically have. And crucially, the directions were wrong. They were coming up through the Earth, not down from the sky. Could they be instrumental artifacts? Some glitch in the electronics or data processing? No. The events were clean. Multiple optical modules had triggered in patterns completely consistent with single high-energy particles traversing the detector volume. The timing was precise. The Cherenkov light patterns were exactly what you'd expect from fast-moving charged particles. These were neutrinos, cosmic neutrinos, from beyond the solar system, from beyond the Milky Way galaxy. Elena was in her office at Berkeley when she received the email from the team at the South Pole. She read it 3 times to make sure she understood. Then she picked up the phone and called Frances Halzen, who had officially retired but remained deeply involved with the project. "Frances," she said, trying to keep her voice steady, "we've got 2 events, both over 1 PeV, cleanup going tracks, high energy, unmistakable." There was a pause on the other end of the line. "Run every check again," Halzen said, his voice quiet but intense. "Triple check the calibration. Quadruple check the background estimates. I'm not publishing until we're absolutely, completely 100% certain." 3 months of verification followed. Every aspect of the events was examined in excruciating detail. The team looked for any possible way the data could be wrong, any systematic error, any background process that could mimic the signal. The events held up. Every test confirmed them. The collaboration affectionately named them Bert and Ernie after the Sesame Street characters. It was a tradition in particle physics to give playful names to the first events of a new type. These were the highest energy neutrinos ever observed. Their energies were so high that they could only have been produced by astrophysical processes involving extreme acceleration. Black holes, perhaps, or jets from active galaxies, or something even more exotic. Their origin was clearly astrophysical. They had come from somewhere out in the cosmos, from some violent event that had accelerated particles to energies that dwarfed anything humans could achieve. But where exactly 2 neutrinos weren't enough to point to a specific source. The directional uncertainty for each neutrino was a few degrees. That might not sound like much, but in the sky, a few degrees encompasses thousands of galaxies. Which one had produced the neutrino? There was no way to tell from just two events. Elena addressed the collaboration at a meeting later that year. More than 300 physicists from dozens of institutions spread across continents, all gathered via video conference. 2 is a hint, she said, looking into the camera. 20 is a discovery. 100 is a map. We keep running, we keep listening, we accumulate more events. Eventually, we'll have enough statistics to start identifying sources. Over the next 4 years, the count grew. By 2017, IceCube had detected 82 high-energy neutrinos, each one a messenger from the deep cosmos. Each one carrying information about violent processes in environments so extreme that matter behaves in ways we can barely comprehend. But frustratingly, most of them couldn't be traced to specific sources. The directional uncertainties were too large. The sky is vast. Picking out the one galaxy among thousands that had produced a particular neutrino was nearly impossible. Until September 22nd, 2017. On that day, everything changed. The alert came at 20 hours, 54 minutes, and 30 seconds, Coordinated Universal Time. IceCube's automatic detection system registered a high-energy neutrino event. The data was processed in real time by computers at the South Pole. Within seconds, the algorithms had determined this was a good event. High energy, clean track, well-reconstructed direction. Energy 290 tera-electron volts. Not quite as high as Bert and Ernie, but still enormously high. Higher than anything terrestrial. Direction right ascension 77.4 degrees, declination plus 5.7 degrees. Direction uncertainty approximately half a degree. The automated system immediately generated an alert and sent it out to a global network of telescopes. Gamma-ray telescopes like Fermi in orbit, ground-based gamma-ray telescopes like MAGIC in the Canary Islands and Veritas in Arizona, optical telescopes, radio telescopes, X-ray satellites, observatories across the electromagnetic spectrum on every continent and in orbit around Earth, all on standby for exactly this moment. The message was simple. IceCube has detected a high-energy neutrino from this location in the sky. Direction attached. Look there. Now. This was the dawn of multi-messenger astronomy, using multiple types of cosmic messengers, neutrinos, and photons, and eventually gravitational waves all together to observe the same event. Elena was at Berkeley sitting in a seminar, half listening to a graduate student present results on neutrino oscillation parameters when her phone buzzed. She glanced at the screen discreetly. IceCube alert, high energy event, follow-up requested. She stood up, muttered a quiet apology to the speaker, and walked quickly out of the seminar room, her heart pounding. In her office, she pulled up the event data on her computer. The display showed the detector geometry, a three-dimensional representation of IceCube with colored dots indicating which optical modules had been triggered and when. The event looked beautiful, clean track, strong signal, high energy deposition, good angular reconstruction. She immediately started sending emails to the leads of the various telescope collaborations. This is a good one, she wrote. Clean high energy, well reconstructed direction. Priority follow-up recommended. Check coordinates attached. Within hours, responses started coming in. Within 24 hours, the picture started coming together. The Fermi Gamma-Ray Space Telescope, which had been continuously monitoring the entire sky, checked its recent data for the coordinates IceCube had provided. There was a gamma-ray source at that location, and it was flaring, producing far more gamma rays than usual. The source was cataloged as TXS0506+056, a blazer. MAGIC and Veritas ground-based telescopes that detect very high-energy gamma rays swung their mirrors to observe that patch of sky. They confirmed it. Very high-energy gamma rays, coming from TXS0506+056. The object was in an active flaring state. Optical telescopes identified the object in detail. A galaxy, 4 billion light-years away, with a supermassive black hole at its center. A black hole with a mass of billions of suns. Matter falling into the black hole formed an accretion disk, a swirling vortex of superheated gas spiraling inward. The temperature in the disk reached millions of degrees. The magnetic fields were intense beyond anything found in nature, anywhere in our solar system. Perpendicular to the disk from the poles of the black hole, relativistic jets shot outward. Streams of matter and energy accelerated by processes we still don't fully understand to speeds of 99.99% of the speed of light. One of those jets was pointed almost directly at Earth. This is what a blazer is. A galaxy with an active supermassive black hole whose relativistic jet happens by pure chance to be aimed in our direction. We're looking down the barrel of a cosmic particle accelerator 4 billion light years away. An ice cube had caught a neutrino from it. Elena sat in her office, surrounded by data displays, seeing the same source identified by multiple independent telescopes using completely different techniques, and she understood what had just happened. They had traced a cosmic neutrino back to its source. For the first time in history, they knew exactly where a high-energy cosmic neutrino had come from. She picked up her phone with shaking hands and called Frances Halsen. "Frances," she said, her voice breaking slightly with emotion. "We did it. We traced a neutrino to its source. TXS 0506 plus 056. A blazar, 4 billion light years away. Multiple telescopes confirming, gamma rays optical radio, all pointing to the same object. We actually did it." There was a long silence on the other end of the line. Then Halsen's voice, thick with emotion, decades of work culminating in this moment. "Elena, my God, we actually did it." The discovery made international headlines. Science magazine called it one of the top scientific breakthroughs of 2017. Neutrinos from monster black hole, scientists solve cosmic mystery. Ice cube detectors traces ghost particle to source 4 billion light years away. The Ice Cube collaboration published the results in the journal Science. The author list included more than 400 names. Everyone who had contributed to building the detector, calibrating it, developing the analysis tools, operating the observatory. But for Elena, the real breakthrough came a few weeks later when the team did something obvious that nobody had thought to do earlier. They went back through the archival data, all the data Ice Cube had collected since 2011, 7 years of continuous operation. And they asked, were there other neutrinos from the direction of TXS 0506 plus 056 that we didn't notice at the time? The analysis took weeks. They had to carefully account for backgrounds, for the chance probability of seeing neutrinos from any particular direction by pure coincidence. And they found something extraordinary. Between September 2014 and March 2015, during an earlier flaring episode of the blazar that optical telescopes had documented, Ice Cube had detected 13 neutrinos from the direction of TXS 0506 plus 056. 13 neutrinos, over 6 months, all from the same source, all sitting in the data unnoticed for years. The probability of 13 neutrinos clustering from one direction by chance was less than 1 in a million. This wasn't coincidence. This was a real signal. "We weren't listening carefully enough," Elena said at a press conference announcing the archival results. "The universe has been sending us messages for years. TXS 0506 plus 056 was screaming at us in neutrinos during its 2014 flaring episode. We had the data. We just didn't know how to listen yet. We didn't know what we were looking for." She paused, looking out at the journalists and scientists in the audience. "But we know now, and we're listening." The detection of Ice Cube 170922A and the identification of its source confirmed by the archival access from 2014 to 2015 marked a turning point. This wasn't just neutrino physics anymore. This wasn't just detecting neutrinos to study neutrino properties. This was neutrino astronomy, using neutrinos as messengers to observe and understand the universe, using neutrinos to see things that photons can't show us. Photons had been humanity's astronomical messengers for all of recorded history. Every culture that has ever looked up at the night sky has done astronomy with light, visible light for most of history. Radio waves, infrared, X-rays, gamma rays, as technology advanced through the 20th century. Gravitational waves detected for the first time in 2015 by LIGO added a second messenger. The ripples in space-time from colliding black holes and neutron stars. Neutrinos were the third messenger, and they carried information that neither photons nor gravitational waves could provide. Because neutrinos emerge unscathed from environments so dense and violent that light cannot escape. From the cores of stars, from the hearts of supernovae, from the immediate vicinity of black holes where photons are bent and distorted and absorbed. Neutrinos fly straight through everything, which means they carry pristine information from their point of origin. No scattering, no absorption, no distortion. A neutrino detected at Earth from a source 4 billion light years away has traveled in a straight line for 4 billion years without interacting with anything. It carries information directly from the relativistic jet of a blazar, from an environment where particles are being accelerated to energies we can barely imagine. This is the future of astronomy. Not just photons, not just gravitational waves, but all three messengers working together. Multi-messenger astronomy. and Elena Castellano had helped build the instrument that made neutrino astronomy a reality. In October of 2026, Elena's phone rang at 5:30 in the morning. She was 63 years old now. Her hair had gone gray. The lines on her face told stories of decades spent in extreme environments, under extreme stress, pushing the boundaries of what humans could observe. She had spent the last 9 years since the TXS 0506 plus 056 discovery, analyzing more ice cube data, identifying more neutrino sources, publishing papers, training the next generation of neutrino astronomers. She was in bed in her apartment in Berkeley when the phone rang. The voice on the other end had a Swedish accent, formal, precise. "Is this Dr. Elena Castellano?" "Yes," she said, suddenly completely awake despite the early hour. "This is the Royal Swedish Academy of Sciences. We are pleased to inform you that you have been awarded the Nobel Prize in Physics jointly with Professor Francis Halzen and Professor Takaaki Kajita Nakamura for the discovery of high-energy cosmic neutrinos and the establishment of neutrino astronomy." Elena sat in silence for a moment, the phone pressed to her ear, the words sinking in. Nobel Prize for neutrino astronomy, for Ice Cube, for 13 years of work, 5 Antarctic summers, a failed marriage, missed birthdays, endless struggles with funding agencies and skeptical colleagues and equipment failures, and the simple, brutal difficulty of building something unprecedented. All of it validated in a single phone call. "Thank you," she managed to say. "Thank you." She hung up the phone and sat on the edge of her bed trying to process what had just happened. Then she called her daughter. Lily was 29 now, not 27, as Elena had mistakenly thought earlier. An aerospace engineer working at SpaceX in Hawthorne, California, designing guidance systems for rockets that would one day perhaps carry humans to Mars. The phone rang 4 times before Lily answered, her voice groggy with sleep. "Mom, it's 5:30 in the morning. What's wrong?" "Nothing's wrong," Elena said, and she started to laugh, tears streaming down her face. "I got the call, Lily, the call from Stockholm." There was a pause. Then Lily's voice, suddenly wide awake, rising to a scream of joy. "Mom, oh my God, Mom, the Nobel Prize!" "Yes, sweetheart, the Nobel Prize." Lily was crying now too, crying and laughing and shouting all at once. "I'm so proud of you, Mom. I'm so proud. I know it wasn't easy. I know what you gave up. I know what it is to..." Elena closed her eyes, thinking about all those missed birthdays, all those months away, all those years when Lily had needed a mother and Elena had been on the ice, or in meetings or analyzing data. "I'm sorry I wasn't there more, Lily. I'm sorry for all the times I chose the work over you." "Stop," Lily said firmly. "You showed me what dedication looks like. You showed me what it means to push boundaries. You built something that will last for decades. You opened a new window on the universe. That's incredible, Mom. That's worth something." "I wish your father could see this," Elena said quietly. "He would be proud too," Lily said. "Even after everything, he would be proud." They talked for another 20 minutes before Lily had to get ready for work. After hanging up, Elena sat alone in her apartment as the sun began to rise over Berkeley, thinking about Raymond Aldrich Davis, who had waited 32 years in a mine for vindication. Thinking about Wolfgang Pauli Brenner, who had bet champagne against his own idea. Thinking about all the physicists who had spent their lives chasing ghosts. And now she was one of them. A Nobel laureate, recognized for seeing the invisible. In December of 2026, Elena stood in the Stockholm Concert Hall, the gold Nobel medal heavy around her neck, and delivered her acceptance speech to an audience that included the King of Sweden, members of the Swedish Academy, physicists from around the world, and journalists covering the ceremony. She had thought about this speech for weeks, written it, rewritten it, discarded entire drafts and started over. She wore a dark blue gown. Her hair was styled elegantly. She looked the part of a Nobel laureate, but when she spoke, her voice carried the same directness it always had. No pretension, no false modesty, just clarity. In 1930, she began, Wolfgang Pauli Brenner proposed a desperate remedy, a particle that could save energy conservation, but that he believed could never be detected. In 1956, it was found. In 1987, it whispered secrets from a dying star, 168,000 light-years away. In 2001, it solved a 32-year mystery about the sun. And in 2017, it pointed us to a monster black hole 4 billion light-years away, proving that neutrino astronomy is not just possible, but essential. She paused, letting the progression sink in. I stand here tonight not as a lone genius, but as part of a chain. Wolfgang Pauli Brenner proposed the neutrino. Enrico Fermi Moretti named it and built the theory. Frederick Reines Caldwell and Clyde Cowan Montgomery caught it. Raymond Aldrich Davis counted it for 32 years in darkness and doubt. Takaaki Kajita Nakamura discovered it oscillates. Arthur McDonald Thornhill proved all the sun's neutrinos arrive just in different flavors. Masatoshi Koshiba Yamamoto heard a star scream. And my colleagues and I built IceCube and traced neutrinos to their cosmic sources. Her eyes scanned the audience. This medal belongs to every graduate student who spent cold months at the South Pole, keeping the detector running. Every engineer who fixed broken equipment at -70 degrees Fahrenheit. Every physicist who believed that listening to the universe in neutrinos was worth dedicating a career to. She took a breath. Our message to young scientists is this. The universe rewards patience. It rewards stubbornness. It rewards the willingness to spend years, decades, even pursuing something others dismiss as impossible. Raymond Davis waited 32 years. I waited 13. The timescales are different, but the principle is the same. Don't give up. The universe has secrets. It will reveal them, but only to those patient enough to listen. The applause was warm, sustained. Elena looked out at the audience and continued. There are still mysteries. We have not yet detected the cosmic neutrino background, the relic neutrinos from 1 second after the Big Bang. We do not know the exact masses of the 3 neutrino flavors. We do not know if neutrinos are their own antiparticles, which would make them unique among all known matter particles. And we do not know if neutrinos hold the answer to the deepest question in cosmology: why does matter exist instead of antimatter? Why is there something instead of nothing? She let that question hang in the air. But we're working on it. Experiments around the world are searching for answers, and we're listening with bigger detectors, better instruments, more sophisticated analysis techniques. We will find the answers. It may take years, it may take decades, but we'll find them. She stepped back from the podium to thunderous applause. Later that evening during the Nobel banquet, as Elena sat at a table with other laureates and members of the Swedish Academy, her phone buzzed with a message. She glanced at it discreetly. It was from a colleague at Princeton. The Ptolemy experiment designed to detect the cosmic neutrino background. Preliminary results: 2.7 sigma excess consistent with relic neutrino capture. Not discovery threshold yet, but promising. Analysis ongoing. Thought you'd want to know during your week in Stockholm. Congratulations on the Nobel. Lena smiled and put the phone away. The next generation was already at work. The cosmic neutrino background neutrinos from the very first second after the Big Bang might be within reach. She thought about Raymond Davis, who had died without seeing neutrino oscillations confirmed. She thought about Wolfgang Pauli Brenner, who had died just 2 years after his ghost particle was discovered. Science was a relay race. You run your leg, you pass the baton, someone else carries it forward. And someday someone would cross the finish line and answer the questions that still remained. Right now, as you hear these final words, about 100 trillion neutrinos are passing through your body every single second. They stream through your skin, your bones, every atom you're made of. 65 billion of them came from the heart of the sun, born in fusion reactions 8 minutes and 20 seconds ago. They traveled 93 million miles and passed through the entire Earth to reach you. They're the same neutrinos Raymond Aldrich Davis counted one by one in darkness for 32 years. Some came from cosmic ray collisions in the atmosphere above you, produced when high-energy protons from distant supernovae slammed into oxygen and nitrogen molecules. These are the neutrinos Takaaki Kajita Nakamura used to discover oscillation. Some came from radioactive decays in the uranium and thorium in the rocks beneath your feet, elements that have been decaying for billions of years, contributing to the heat that keeps Earth's core molten. Some came from nuclear reactors thousands of miles away, fission reactions splitting uranium atoms and releasing floods of antineutrinos. The descendants of the neutrinos, Frederick Rhinus Caldwell and Clyde Cowan Montgomery, first caught in 1956. Some came from a supernova that exploded in a galaxy you will never see, perhaps hundreds of thousands of years ago. Their neutrinos finally reaching Earth after an incomprehensible journey through intergalactic space. Like the 25 neutrinos from supernova 1987A that Masatoshi Koshiba Yamamoto detected. Some came from a blazar 4 billion light-years away from the relativistic jet of a supermassive black hole, particles accelerated to energies that dwarf anything achievable on Earth. The neutrinos, Elena Castellano, and the IceCube collaboration traced to their source. And roughly 336 neutrinos in every cubic centimeter of space around you, in the air, in the space between atoms everywhere, have been drifting since 1 second after the Big Bang. They are the oldest particles in existence, Aside from photons from the cosmic microwave background, ancient travelers from the birth of the cosmos. They decoupled from matter when the universe was 1 second old, when the temperature was 10 billion degrees, when there were no atoms, no stars, no galaxies. They have been drifting for 13.8 billion years, cooling as the universe expanded, their wavelengths stretching, their energies dropping to almost nothing. Not one of the neutrinos passing through you right now will touch you. You will never feel their presence. The electromagnetic force that builds your body and shapes your world has no hold on them. They exist in a realm of physics that your senses were never designed to access. They pass through you, through the earth, through stars, through light years of lead without noticing. And yet you know they are there. You understand what they are, where they come from, why they pass through everything. You've grasped a truth about the universe that is invisible, intangible, accessible only through the power of human reasoning and human stubbornness and human patience. The neutrino doesn't know you exist. It has no awareness, no intent, no knowledge of the matter it passes through, but you know it exists. And in the quiet contest between a cosmic force that ignores almost everything and a human mind that seeks to understand everything, the mind wins. Not by stopping the neutrino. Nothing can truly do that. But by knowing it's there, by measuring it, by using it to peer into the hidden architecture of stars, by using it to witness the death of stars in distant galaxies, by using it to see the structure of the early universe, by using it perhaps to understand why matter won its ancient war against antimatter, why the universe is filled with atoms instead of emptiness. This is the story of the neutrino. Born from Wolfgang Pauli Brenner's desperate idea to save energy conservation in 1930, when he bet champagne it would never be found. Named affectionately by Enrico Fermi Moretti in 1933, who built the theory that explained how it worked. Caught for the first time by Frederick Rhinus Caldwell and Clyde Cowan Montgomery in 1956, proving the ghost was real. Counted patiently for 32 years by Raymond Aldrich Davis in a mine in South Dakota, measuring a deficit that nobody understood, enduring doubt and criticism, waiting for the universe to reveal its secret. Discovered to oscillate by Takaaki Kajita Nakamura in 1998, proving neutrinos change flavor and have mass. Proven to account for the full solar flux by Arthur McDonald Thornhill in 2001, solving the 32-year mystery. Detected from a dying star by Masatoshi Koshiba Yamamoto in 1987, arriving 3 hours before the light, announcing stellar death. Traced to a supermassive black hole by Elena Castellano, and the Ice Cube collaboration in 2017, opening the era of neutrino astronomy. And still holding secrets about its own nature, about whether it is its own antiparticle, about whether it explains why anything exists at all. The universe built a particle that barely participates in reality as we experience it. And then on one small world orbiting an ordinary star in an ordinary galaxy, reality built something that could notice. The ghost particle and the curious species. Both made of atoms forged in stars. Both governed by the same laws. Both part of the same cosmos. One passes through everything. The other tries to understand everything. And somehow, improbably, beautifully, they found each other. So tonight, when you look up at the stars, remember what's invisible. The neutrinos streaming from every point of light you see. The neutrinos from the Big Bang, older than galaxies. The neutrinos from dying stars, from black holes, from cosmic cataclysms. Billions of light years away. They are all around you. They have always been around you. They will always be around you. You cannot feel them. You never will. But you know they're there. And that knowing, that understanding achieved through decades of patience by people who dedicated their lives to seeing the invisible is a victory. In the contest between cosmic forces and the human mind seeking to comprehend them, the mind wins. Not through force, not by stopping what cannot be stopped, but through understanding, through measurement, through patience, through the stubborn refusal to accept that anything in the universe is truly unknowable. The neutrino is no longer a ghost. It is a messenger, and we have learned to listen.